So this video will be a little bit longer. This is what we're going to do here is we're going to interpret proton NMR spectra. So let's say we've got a little spectra here. And we have a little peak here. That's our standard 0. And let's say we've got a peak with a relative area of 3 underneath it, with a chemical shift of 2.2, and another peak up here with a relative area compared to this one of 1, so it's a 1:3 ratio, with a chemical shift of 9.7. So we know that this is a 1:3 integration ratio. Now, if the molecule was ethanol, we know that there's 2 hydrogen environments. There's one and there's the other. So we can see straight away that this environment here must correspond to these 3 hydrogens, and this environment must correspond to this hydrogen here. Let's say we didn't know what the structure was at all. Now, we know that this environment here has got 1 hydrogen in it, and it's 9.7. So we take our data sheet, we look for 9.7, so it's going to be this structure here, and it's going to have 1 hydrogen in it. So you know that this one here is going to be that. And we've got another peak here at 2.2, so we'll find 2.2 in our list. So the only thing it can be is this one here. However, because the integration ratio is 3, there'll be 3 times as many hydrogens as this one. So there must be 3 hydrogens in here. So I'm not just going to copy that down. I'm going to copy it down, but with 3 hydrogens here like this. So we know a structure must contain that and that in. So the only thing it can be is ethanol. Now something a bit more complicated than this. Okay, we're going to look at spin-spin coupling now. Sometimes called spin-spin splitting or splitting. Okay, and this is what happens when we zoom in on NMR peaks, and the peaks themselves are actually split up into further smaller peaks. And this happens because the magnetic field felt by any hydrogen is affected by the magnetic field on the hydrogen atoms that are on neighbouring carbon atoms. We call them adjacent hydrogens. And this spin-spin splitting gives information about the neighbouring hydrogen atoms. So not only about these hydrogen atoms, but the ones adjacent to those ones. Not only about these ones, but actually the ones adjacent to that one. So actually tell you about the hydrogens next to the hydrogens that you're looking at, which is quite useful. And carbon NMR doesn't do this. So this is the advantage of proton NMR over carbon NMR. That proton NMR has spin-spin splitting patterns, which gives more information than carbon NMR. Of course, carbon NMR gives information about carbons. Obviously, you don't get that from proton NMR. So often they're used together to work out the structure of a molecule. Okay, now there's something called the N+1 rule. Now I'm going to write down the N+1 rule and then we're going to apply it. I'm going to read that out now, but it might not mean much to you just yet, but just write it down, we'll come back to it. The N+1 rule is N hydrogens on an adjacent carbon atom will split a peak into N+1 smaller peaks. Okay, well, let's use this spectra here as an example. So I'm going to redraw it again below. Now the TMS peak won't be split because that's on a separate molecule. But if we look really, really carefully to this peak here with an integration ratio of 1, it's actually split up into 4 smaller peaks, which look a little bit like this. 1, and then 2 bigger ones up here, 2, 3, then the 4th one down here, 4. So this, when we look carefully at it, if we were to magnify this out, it would be split up into 4 smaller peaks. This particular one here will actually be split into 2 peaks. Both the same size. That one, remember, had the integration ratio of 3. That was at 9.7. That was at 2.2. I've exaggerated these a little bit just so you can see them a bit clearer. So let's start off with this one here. So we've got a peak here at 9.7. So we know that this was the hydrogen here. This peak is split into 4 further peaks, and the N+1 rule tells us, because it's 4 peaks, now N is equal to 4. N is not equal to 4. On the adjacent hydrogen, so this is the peak we're talking about here, hydrogen, on the adjacent carbon, so this is the carbon we're talking about, with that hydrogen, corresponds to this peak here, with the integration ratio of 1 hydrogen. Now that carbon is attached to another carbon, which has got 3 hydrogens attached to it. Therefore, N is equal to 3. So N equals 3. So N plus 1, so that would be 3 plus 1 equals 4. That's why it's split into 4 peaks. 4 smaller peaks. Okay, let's have a look at this hydrogen environment here. Now we know the integration ratio is 3 and it's 2.2 parts per million. So if you remember, that was this environment here, and the integration ratio was 3. There's 3 hydrogens here. So on the molecule, it's this one here. So that one was 2.2, and that one there was 9.7. Now in this case, we've got an environment here, which is next to a carbon that is attached to 1 hydrogen. So we're talking about this environment, but it's next to a carbon which is attached to 1 hydrogen. Instead of saying the word next to, sometimes we use the word adjacent. So N, because there's only 1 hydrogen here, N is equal to 1. N equals 1. So using the N+1 rule, that's 1 plus 1 equals 2. So here we have 2 peaks. So it's split further into 2 peaks. We call that a doublet. A doublet is when you split into 2 peaks. When we split something into 4 peaks, we'll call that a quartet. A triplet not part of this molecule, would be where you've got it split into 3 peaks. Now, at A level, you won't have to interpret any spectra that has been split into 5 or more peaks. It's only going to be singlet, which is where there's 1 peak, which means that there's no adjacent hydrogens. Doublet, 2 peaks, which means that there is 1 adjacent hydrogen. Triplet, which is 3 peaks, which means that there's 2 adjacent hydrogens. And quartet, which means it's split into 4 peaks, which will be 3 adjacent hydrogens. Okay, let's do another example. So that's quite a complex rule. Remember, it's the n+1 rule, not the n rule. So the next one that we're going to have a look at is propanoic acid. So I'm going to go straight in at drawing the splitting pattern of the proton NMR. Standard tetramethylsilane, we've got a triplet there, so that's a triplet, and that value there is 1.1. So it's a 1.1 triplet, and the integration ratio here is 3. We have another peak at 2.4, and the integration ratio is 2, and this one is a quartet. Those are the 4 peaks, 1, 2, 3, 4. And up here we have the final peak with an integration ratio of 1, and that is at 11.7, and you can see there's only 1 peak there, so that's a singlet. Now, when you're analysing these, it's useful to write this information below it. So if you get a picture of this in the exam, you might not actually get the word singlet, quartet, triplet, etc. written below that. Okay, so I'm going to use the n+1 rule here and apply that to this. So if it's a singlet, then n is equal to 0. Quartet, n is equal to 3. A triplet, n is equal to 2. Remember, n is the adjacent hydrogens. Okay, so we've got quite a bit of information here now. We've got the integration ratio, which will tell us the ratio between the hydrogens in each environment. And also, we've got the number of adjacent hydrogens as well. So we've used this information here, singlet, quartet, triplet, to work out the integration, the adjacent hydrogens. And we've used the integration ratio to work out the relative number of hydrogens in each environment. Now, we haven't used these numbers here, the chemical shift in parts per million, and it's a data sheet that we need to use for these. So let's have a look at our data sheet. So what we've got here, we've got a singlet at 11.7 parts per million chemical shift. So let's find 11.7 on our sheet. So 11.7 here must be the H attached to a carboxylic acid. So this is down to a COOH group. It has to be. Now, we've got another peak here at 2.4. So let's find 2.4 on our list. So what have we got? It's going to be this one here. So it's going to be a hydrogen, which is chemically bonded to a carbon, which is attached to a carbonyl. But instead of just drawing that picture down straight away, I'm going to have a look at my integration ratio. Look, at integration ratio here is 2. So there's actually 2 hydrogens attached to this carbon. So it's going to be a CH2 group here, like that. That's that H there, remember. Now we've got the triplet here with integration ratio of 3. So this is at 1.1. Now if you've got a peak at 1.1, it's either going to be an amine, it's unlikely it's going to be that. In this case, it's going to be this RCH3 group. So our integration ratio is 3. So I'm not just going to write down C with 1 hydrogen. It's going to have 3 hydrogens coming off it like this. So I know that our molecule is going to have this in it, that in it, and that in it. It's going to have a CH2 next to a carbonyl. It's going to have a CH3 in it, and it's going to have a carboxylic acid group in it. So I know that it's going to contain those 3 things. Now, what we need to then do is we need to be able to join these together. So we know we've got a singlet. Now a singlet means that the adjacent carbon has, the adjacent atom has no hydrogen attached to it. So to begin to build up our molecule, so this is this group here. I know this is correct. Now that hydrogen there is attached to that oxygen. Now because this is a singlet, N is equal to 0, which means that there's no hydrogens here. So N is equal to 0 there. I've just labelled that N is equal to 0. Then we've got this C double bond O, which is the C double bond O here, and we've got a CH2 here. So I'm going to write down my CH2 there, which is correspond to this one here. Now we know that N is equal to 3. Okay. Oh, I should label that. Sorry, N is equal to 0. It's this hydrogen we're talking about. So there's no hydrogens attached to that carbon there relative to that one. Now this one is the CH2 here. And that is N is equal to 3. So which means that there must be a carbon on this side attached to 3 hydrogens. So N is equal to 3. And it so happens that when we come to this one, we need a CH3, there's our CH3, and N is equal to 2. So next to this environment here, we've got an N is equal to 2. So that's this one. And that all fits. So I've got, just to summarise, 3 different hydrogen environments. 1, 2, 3. So 3 distinct peaks. An integration ratio of 1 to 2 to 3. 1 to 2 to 3. We've got 11.7, which is a carboxylic acid. 2.4, which is hydrogen next to a carbonyl. 1.1, which is a CH3 group on its own over here. We have a singlet. The reason why I have a singlet, this one here is a singlet, is because its adjacent atom has no hydrogens attached to it. We've got a quartet over here, and that's because its adjacent carbon has got 3 hydrogen atoms attached to it, and we've got a triplet. This would be a triplet because its adjacent carbon has got 2 hydrogens attached to it. Remember, it's adjacent hydrogens that we're looking at, not the actual hydrogens that's attached to that carbon, because that will be the integration ratio. Okay, so that would be propanoic acid. Let's have a look at our solvents for proton NMR now. So NMR is normally run in solution. The solvent must not contain any hydrogen atoms. I hope that's very clear, because otherwise the signal from the hydrogen atoms in the solution of the solvent would swamp the signals from the hydrogen atoms in the sample, because there's more of them. Okay, so it mustn't contain any hydrogen atoms. That's our first thing. So one common solvent is this molecule here. CCl4, which is tetrachloromethane. So this doesn't have any hydrogens in there. Or otherwise, if you need a hydrogen molecule, you don't have to use hydrogen. You can use another isotope of hydrogen, because this isotope of hydrogen, deuterium, is not detected by NMR. Because this is proton NMR, isn't it? Which is this isotope of hydrogen. So instead, let's say we think that this particular solvent is an excellent solvent for that particular compound. Obviously we couldn't use that, so instead we can use what we call the deuterated version of that sample. So instead of writing 2H like this, we can replace that with a D, which stands for deuterium atom. Okay, so deuterium, remember, doesn't produce a signal in proton NMR. So this one is CdCl3. Or let's say water is a great solvent for the particular compound. Obviously we couldn't use water. Instead we can use D2O like that. And if something like benzene would have been an excellent solvent, we wouldn't use that. We would use C6D6 instead. Okay, so I'm going to do a couple more examples of interpreting and predicting NMR spectra. So let's have a look at propanone now. So the NMR spectra of propanone, if we look at the structure here, now if this was a carbon NMR, done this in a previous video, we know it has 2 peaks because there's 2 different carbon environments. That's one environment, that's the second. Okay, but with a proton NMR, it just has 1 peak. That's because all of the hydrogens are in one environment. They're identical hydrogens. And the chemical shift value would be something like 2.1 parts per million. So 2.1 parts per million would tell us that the hydrogen is on a carbon adjacent to a carbonyl. So here we've got hydrogens on a carbon adjacent to a carbonyl carbon here. So 2.1 parts per million, up to 2.6 parts per million. Okay, and again it would be a singlet as well, wouldn't it? It would be a singlet because look at our hydrogen environment here, look at the carbon it's attached to. The adjacent carbon has no hydrogens attached. Go from this side as well. The adjacent carbon has no hydrogens attached. So that would be a singlet, okay? Now, let's look at a bit more complicated one now. So we're going to look at ethyl ethanoate. Which we know is an ester, okay? Let's draw the structure. Okay, now there are three different hydrogen environments in this molecule. So we've got this one, and that one. Now it's important to stress that this hydrogen environment is different to that one. Yes, they're both CH3s. However, this is a CH3 attached to a carbon-carbon, but this is a CH3 attached to a CH2. So they're going to have different chemical shifts. Now let's have a look at the integration ratio. The integration ratio between these peaks, if we call this one peak A, that one peak B, and that one C, the integration ratio would be 3 to 2 to 3. So the area underneath the peak would be 3 to 2 to 3, because this one has 3 hydrogens, this one has 2, and this one has 3. Okay? Now, this one here would be a singlet. And the reason why that one will be a singlet is because its adjacent carbon has no hydrogens attached to it. So N is equal to 0. Remember the N plus 1 rule. So N is 0 plus 1, that's a singlet. B. Peak B would be a quartet. And here N is equal to 3. So B, peak B would be a quartet because N is 3, because the adjacent carbon has 3 hydrogens attached to it. So N is 3. So N plus 1 is 4, that makes it a quartet. Environment number C will be a triplet. So in this case, N is equal to 2. Now if N is equal to 2, because there's 2 hydrogens here, we're talking about this environment, the adjacent environment, N is equal to 2. So 2 plus 1 is 3. That's going to be a triplet. Now let's have a look at the chemical shift ranges. So we'll get our data sheet out here. So we've got a CH3 attached to a carbon-carbon. So we're looking for hydrogens attached to a carbon-carbon. So let's find our carbon-carbons. Now there's one there, so but it can't be this one because this one has got an O attached to a carbon-carbon. It could be this one. This one has got a hydrogen attached to a carbon-carbon here. However, this one is for an aldehyde, not an ester. Okay, so we're looking for an ester here. Now it's not this one, even though this is an ester structure, because if you look at the position of this hydrogen here, attached to a carbon that's attached to the oxygen. So we're talking about this one here really. So it's not that one. We're going to look at this one here. It's this one here. So we've got a hydrogen attached to a carbon next to a carbon-carbon here. Okay, now this one here is the correct one. So we've got 3 hydrogens attached here. 1, 2, 3. So you probably get a peak here, a singlet, at somewhere between 2.1 and 2.6. Okay, we've got a CH2 here, which is our quartet. Now our quartet there is a CH2, so we've got looking for a CH2 which is attached to an O, then a CO. So hydrogens attached to a carbon which has got an O and then a CO. So it's going to be this one here, O and then CO here. So this one is somewhere between 3.7 to 4.1. And the last one here, our triplet, this is just a regular CH3. So it's this one, 0.7 to 1.2. Okay, so let's just recap this. 3 different environments here, 1, 2, 3, labelled A, B and C. An integration ratio of 3 hydrogens, 2 hydrogens, 3 hydrogens. This one is a singlet because the adjacent carbon has no hydrogens, so N is equal to 0. So N plus 1, 0 plus 1 is 1 singlet. Here, 2 hydrogens, it's going to be a quartet because the neighbouring carbon has 3 hydrogens, so it's going to be N is equal to 3. And here we have a triplet because the neighbouring carbon hydrogen environment N is equal to 2. So we add one on and we get a triplet. And then we've got our parts per million values directly from our data sheet. So that is the carbon NMR of ethyl ethanoate. So a little bit more complicated, that one.